today's class would be on a topic which is more of practical importance. So I believe it's easy when we say practical. It's easy to look at, and there are few concepts which at least for examination point of view, those concepts are pretty important to because many questions can be framed on those questions. So I would like you to look, at least spend the next 1 hour very carefully listening to what is being displayed. You can easily download this file by right clicking, and you can download it on your server. There's an announcement, very simple announcement for this Friday's class. This Friday there will not be any class. I have to be away for an exam duty. So Friday class is cancelled. However, here at IIT, next week onwards we have our mid-semester exams. I believe many universities, institutes at your place would be having mid-semester exams or something very similar. So I propose that this Friday we have a test. You can come here, you can have a test for 1 hour duration. The question paper, I will email the question paper to your respective teachers. So I request the teachers to, if they are keen to have a test this Friday, I request the teachers to email to me. Okay, email to me, and I'll send the question paper as an attachment to the email along with the answers. So I only request the teachers, because answers will only be given to the teachers, please. So if you're keen, you can have a test this Friday. Okay, our regular class will continue from next week onwards, next Tuesday. Okay, let's begin. In today's compaction, we will look at few important structures. For example, the factors. You look at factors which affect compaction. We'll also look at the difference between compaction and consolidation, which is fairly straightforward. And probably we'll see at the compaction behavior of both fine-grained soils as well as the coarse-grained soils. Okay, next slide. So we all are aware, soils have been used as construction material. Okay, either as highway embankments. So highway embankment, you're probably aware, some embankments are built probably 4 to 6 meters high. An excellent example would be the Golden Quadrilateral, which connects the major metros, major cities of this country. All these embankments are pretty high. They carry huge amount of load on the ground. Even earthen dams is a good example. All these examples require the soil to be well compacted. There are loose fills. So all these loose fills are to be densified to improve the mechanical characteristics, or an example is the shear strength, compressibility, and the permeability. These are the 3 important mechanical behavior we look at. I've got some snaps, some photographs over here which help us to at least look at some of the available compaction equipment in the field. I would like you to look at the bottom left, which is a sheaves foot roller. Sheaves foot roller has high kneading action, very similar to how you knead your flour, when you want to make a chapati or something. That same kneading action is provided by the sheaves foot roller. So it has number of kneading points. Each kneading point it transmits shear stresses of up to few thousands of kPa. It's huge. Compare this to the pneumatic roller. That's a pneumatic tired roller. So pneumatics, we are quite aware is air, compressed air. And if you have been driven a motor vehicle before, a compressed air in a motor vehicle probably varies by about 200 to 300 kilopascal. That's the amount of pressure the air which is filled in the air, the tires, the rubber tires. Maybe your bicycles may have slightly higher pressure, but nonetheless it's few hundred kPa. Maximum, I would say the air can be compressed about 7 to 900 kilopascal. So this is the typical pressure, 700 to 800 kilopascal, which is filled in the tire. So that amount of pressure the tires impose. There is another roller which is not shown over here, is the vibratory roller. These again provide vibrations to the soil in order to shake them, they vibrate them in order to densify the soil. All these equipment which we speak about, let me move to the next slide. All these equipment which we speak about only deal with surface or near surface compaction. When I say near surface, we are only targeting the top 3 meters of the soil, okay, top 3 meters of the earth. If you want to look at deeper ones, you have different tools which compact the soil right up to tens of meters, 10, 15 meter, even going down to 20 meters is not uncommon. They are used using this equipment which is shown by a photograph over here. Some vibratory tool is pushed into the ground. Okay, so if you do a Google search on vibroflotation or even dynamic compaction, wherein a heavy weight is dropped over the ground from 10 meters. So give an example. You have 10-ton weight which falls by a 10 meter. That's dynamic compaction. So you can do a Google search on these two to give you a fair idea of what deep compaction is about. In our syllabus, they are only concentrated on surface or near surface, that is the top 3 meters. So the purpose is you densify the soil. That's the density starts to increase. In this case, we have shown the unit weight of the soil increases because when you compact the soil, the air voids, they get either removed or reduced. There is of course not a total removal of air voids. When you do compaction, any compaction means will not be able to totally remove the air voids. So take an example of the cartoon which is shown on the left hand side. Remember, this is a 3-phase diagram we have seen on the first lecture, it was the second lecture, wherein we had the volume on the left hand side and the weight or the mass on the right hand side. So that's the total volume where solids, water and air. So if I deal with compaction, what it does is it reduces the volume of air. In other words, the top Lego has got compressed, or the height of the top Lego is reduced. The height of the bottom two Legos remain the same. Whereas there is a term called consolidation. It's important to note consolidation can only be studied if it's a 2-phase soil, meaning there is no air. The third Lego does not exist. If it's a 2-phase soil, consolidation would mean you remove the water. In other words, the top Lego gets shortened out in this case. Remember, there is no air. So if I want to really look at a good comparison between compaction and consolidation, it's a good idea to look at the next table. I'll just flip to the next slide, wherein the left hand side are the 4 reasons given for compaction and the right hand side are consolidation. Okay, the first one, compaction is instantaneous, meaning the results, the energy provided and the result are instantaneous. You can monitor the ground immediately after the work is done. Whereas consolidation is time dependent. It may need years to gather for the water to remove. If you look at the second point, the 3-phase diagram we have looked at clearly shows that the soil would be unsaturated. There is air. So the second point, soil is always unsaturated, is true. Whereas consolidation, soil will always be saturated. You can only study consolidation if soil is saturated. In fact, to give you an idea, most of the theory which we follow in soil mechanics, either for shear strength or for compressibility or for permeability, or most of the theory deal with saturated soil. Although, to be honest, saturated soil, it's hard to get saturated soil in the field. Look at the third one. The third one, if I go back, if I slowly go back and look at it, okay, remember the water, the weight of water remains the same and the weight of solids remain the same in compaction. In consolidation, the water gets reduced. In other words, the weight of water gets reduced. So I have to follow this analogy. Let me move to the next slide. The water, because the water gets reduced, I can clearly say or safely say water content on the left hand side compaction, because the air, it's the air which is getting removed, so the water content remains constant in compaction. Okay, whereas the water content reduces in consolidation. The fourth one is the fourth point is more of contractor oriented, meaning the field contractors, they have some specific compaction techniques to be used in the field. So give you an idea of this, let me just go back please 2 slides, where we had the photographs. This photograph over here was a sheep foot roller. It provides large energy. You remember we said few thousands of kilopascal. To give an approximate number, up to 5 to 7,000 kilopascal. Such high energy is required to break the clay clods. You know, clay is to break the clods you need such high energy. In other words, this would be more suitable for clay. Pneumatic is more suitable for silty deposits. A vibratory is more suitable for sandy deposits. Over here we got our old, very commonly seen drum roller. Drum roller, I would say in today's world, at least for embankment construction, would be obsolete. Unless you want to, lay a sub base with lot of gravel, that it needs dead weight. So drum roller only provides dead weight, does nothing. And if you want to do good compaction, you need either pneumatic, cheese foot or vibratory. Some rollers are available in twin. Like I said, this is contractor dominated area. So they are the ones, they are leading us. I would say we at the university level are far behind on what the contractor people they work on. Example is this pneumatic tire roller can have tires at one end, at the other end it can have a vibratory kind of a roller on the same equipment. Let me move to the slide we were on to. So that's the difference. Okay, some specific compaction techniques are used, which is more contractor specific. Consolidation is merely because of a static or a dead load placed over the soil. Compaction in the field is specified. You specify what compaction you would like to achieve in the field by specifying a roller, what roller, how many passes of the roller, and what should be the weight of the roller. Okay, in terms of vibration, what is the amplitude of vibration it should provide. All these are, you specify what because of what compaction you want to achieve in the field. In the laboratory, we specify what is the compactive in the laboratory by looking at the impact of a rammer. It's a rammer which is dropped from a fixed height into a fixed volume of soil. Okay, so we'll look at this second point later. But there are other methods of compaction. Kneading compaction, which is more suitable when you want to compact clays in the laboratory. Kneading, it provides large shear energy. And static compaction is also feasible if you want to just provide large dead load over the soil. Now the photograph over here I have purposely put because it shows 2 persons. If you look at carefully, that's in fact a large mold. Okay, we will probably given a chance to look at the mold, and this is a heavier rammer. Okay, we'll again look at this heavy rammer. It's the modified Proctor rammer, which falls from 45 centimeter height. But that's not the idea of showing this photograph. The idea is when you handle such an equipment, even in laboratory, safety is of more importance. If you look at this, the feet. Okay, I'm not able to show the pointer, please. No, sorry, the writer. The writing? Okay, thank you. So if you look at the feet, okay, not visible. Sorry. Look at the feet, uncovered feet, no shoe. Okay. Now I have seen people lose their finger. They have lost fingers when doing simple compaction tests. For example, this person dropping the hammer, it's quite heavy, 4.9 kg, and the other person sees that there is some soil stuck on the boundary. He or she just puts his hand inside, and therein you lose a finger. Such a thing is very risky. You got to be careful, and there has to be good coordination work. Okay. Okay, so look at the laboratory test. In laboratory test, Proctor in 1933 came out with the first, simple procedure or a simple device to do a Proctor compaction test. This was primarily done because they wanted light planes. Airports were started to develop. Aeroplanes were, were came into picture for, which were helpful for light compact airplanes came in, and they needed to run. They needed to build runways and taxiways. So that's standard Proctor for us. It's a 4-inch collar, dia collar. If you ask me why Proctor had chosen a 4-inch dia collar, which despite coming to about 80 plus years today, if you ask me why did he choose, your guess is as good as mine. Probably he went to the closest hardware shop, and that was the 4-inch pipe was the one he could easily get. And we still follow this. But the idea is, you provide energy. That means you provide a weight, a constant weight which falls from a constant height into the mold. Okay. So in other words, if I look at this carefully, I provide energy, that's mgh, into a constant volume. So if I want to look at this, mgh over constant volume, that's the energy per unit volume, that's joules per meter cube. We may be more familiar with kilogram force meter, that's the energy, mgh, divided by volume. Nonetheless, anything you're comfortable with, the idea is you provide energy per constant volume. In other words, today if I'm not happy with Proctor's, I can modify it. I can change the volume as long as I keep this constant. So I reduce the volume of the soil, I only increase the energy to keep this whole thing constant. And there are people, researchers who have worked in this area. If you do a quick search on mini Jodhpur compactor, probably this works on a similar concept that you have, you're looking at the energy, how much energy you provide, okay, in a unit volume. It becomes focus of different research. If you want to change the volume, and you change likewise, you change the energy. Okay. So the standard Proctor test, what we do is, I hope this expression is visible to you. It's you have done this before. It's dry unit weight equals to bulk unit weight divided by 1 plus water content. Okay. In other words, the mold of the soil which is fixed, it provides the bulk unit weight. So you compact the mold by providing blows over the ground. You compact the mold, soil into the mold, and which gives you a bulk unit weight. And after the test, it provides the you can measure the water content, and this bulk unit weight divided by 1 plus water content gives you the dry unit weight. So if you have this dry unit weight for a different water content, it's easy to plot this in a figure which is on the horizontal axis or the abscissa axis you have water content, and on the vertical axis or the coordinate axis you have the dry unit weight. So if I have this plot, and if I choose a particular, so mix the soil with a particular water content and then compact it, I should get a point which is shown over here. So I have a dry unit weight against water content. The next step would be to change the remove the soil, mix some additional water, meaning you change the water content and then recompact it by providing the same energy. Okay, that gives you a different dry unit weight against water content. Remember, these points have been plotted for the same energy to keep the energy per unit volume constant. Likewise, I can continue this and get a series of points which gives me a shape, a parabolic shape, and I connect the two, form a parabola. Okay, this, if I use the standard Proctor, that means the which in IS equivalent is Indian standard equivalent is IS light compaction. We will look at the specifications of IS light compaction in the next few slides. But nonetheless, you have a standard Proctor which gives an inverted curve, inverted parabola. Okay, and if I join the peak of the parabola, the vertical component or the ordinate component gives the maximum dry unit weight. It's the maximum value. So I have the maximum dry unit weight. The horizontal component or the abscissa component is the water content because it's optimum. It's a transient peak. You fall over there, you fall over there. It's a transient peak. In other words, it's optimum water content, and some people like to call it optimum moisture content. Okay. Now this curve, we say, is unique for a given soil. The method of compaction, okay, meaning if I use either a Proctor, a rammer, or even a steady or constant load, but it's method of compaction which we follow. Or the compactive effort, whether we are using a lighter rammer or a heavier rammer. Okay, look at this rammer in a while. If you're using a heavier rammer, which is heavier rammer for Proctor test was 4.5 kg. I would not like you to remember these figures for the time being because we are more keen into what IS code tells us. So for the modified Proctor compaction, to give you an idea, it's 4.5 kg falls to 457 millimeters, but 5 less. We'll look at this for IS compaction in a while. But the idea is the modified Proctor is much heavier, or it provides more energy for the same volume. So if it provides more energy, you should have a higher dry density. So these are the higher dry density values. And if you look at this carefully, you have a different and a higher maximum dry unit weight and a different optimum water content or optimum moisture content compared to the standard Proctor. Give you a range of values, typical values which you can see in the literature, or if you look at some soil investigation report, this is the range, typical range which you would be looking at. Maximum dry unit weight, that's the peak value. The ordinate value is between 16 and 20 kilonewton per meter cube. Apologize, this is 16 to 20 kilonewton per meter cube. Water content, optimum moisture content is about 10 to 20%. That's the typical range. Let's look at what IS equivalent is, and this is important for us. The IS equivalent to standard Proctor is the weight of the rammer is 2.6 kilograms. It drops to a height of 310 millimeters, and the volume of the soil is 1000 centimeter cube. You provide 25 blows. It's not shown over here. You provide 25 blows in 3 layers in this mold. So the first layer, put a heap of soil approximately 1/3 of the height of the mold, and then compact it using 25 blows. Then you provide grooves into the first layer, and then recompact it using the second heap of soil, and so on up to third heap. IS heavy compaction is very similar, but what you have is you have a heavier rammer which is 4.9 kg. So you need a really strong person to do this, and which drops to a 45 centimeter or 450 millimeter. The number of layers are 5, and it's 25 blows per layer. 25 blows is similar to what IS compaction was. Okay. You provide a heavier energy. There is a term called zero air void line, and I'd like you to look at this carefully. You may recall a relationship between dry unit weight, water content, and specific gravity. If you don't recall, I seriously suggest that you do a lot of problems, and it's a good idea to do a test this Friday. So if you have, I repeat, if you would like to do a test, please do by all means email to me, and I will provide the question paper based on whatever has been covered till last week. Okay, we'll have a simple test for 1 hour duration. Okay, let's look at the relationship we have. Recall dry unit weight is GS gamma W 1 plus E. If you don't remember this, I have said, it's easy to look at the bulk unit weight GS plus SC divided by 1 plus E whole thing times gamma W. This will give you the dry unit weight. Zoom in, please. Okay, over here I have removed S because of, it's dry, so S becomes 1. I can replace E by this SC equals to WGS. Okay, so I have replaced E by WGS by S. Okay, before I continue, it's an interesting question over here. In the numerator, I have GS plus SC and I have removed S, degree of saturation, to be 0 in order to calculate dry unit weight. But I have degree of saturation coming back over here. Okay, it's a question for you to think over. Please think over this. Why this has happened. Okay. So we have this relationship to derive the dry unit weight. It's this relationship, okay, this one. And if I have the data, that's the standard Proctor data, modified Proctor data. It shows OMC as well as the maximum dry unit weight. OMC, maximum dry unit weight for the other curve. And if I have this data, if I plot this data of for degree of saturation 1, when the soil, for saturated soil, what is the dry unit weight? So I have a different value, a fixed value of water content, and I get a dry unit weight value. So water content, if I fix, I have a dry unit weight. So I have points over here. We have plotted 3 points corresponding to a degree of saturation equal to 1. A degree of saturation 1 is 0 air voids. There are no air voids. And if I connect these points, I get 0 air void line. Okay. If you look at this line carefully, the curves will never intersect the line. Okay. So degree. So no, in other words, no matter how much you compact, how much energy you provide, you can never achieve a saturated soil. That's exactly the thing which we spoke about earlier. So just to put it in English, we have 0 air void line for S, or degree of saturation equal to 1. It's the maximum dry unit weight which can be obtained for soil at a given water content. A maximum dry unit weight which can be obtained for a soil at a given water content. It can never be reached in practice. Okay. I also see one more definition coming over here, and I don't mind explaining this right now. If I connect, if I use a different energy, a higher energy, and still a higher energy for the same soil, what I see is I can connect the peaks of the soil to find out the line optimums. It's like a line which connects all the optimum together. You'll find that this line is nearly parallel to 0 air void line. If I rephrase this question, okay, I have 0 air void line corresponding to degree of saturation equal to 1. I can plot another line corresponding to degree of saturation equal to, say, 90%. I can likewise, I can have another line which I can plot corresponding to degree of saturation shown by this broken line. In other words, the line of optimums has a constant, nearly a constant degree of saturation. Okay, nearly. We look at some factors which affect compaction, and it's a good idea to look at, how does water content, the compactive effort, the type of soil, and the method of compaction affect. Firstly, the water content. What we have done over here is this plot, water content versus the dry unit weight. That's the parabolic shape. I have replotted this in vertical axis, meaning the horizontal axis is not shown over here. the top one is low water content. That's somewhere here, low water content. And as I go down the arrow, somewhere over here I've shown optimum moisture content. That's the peak over here, and high water content at the bottom. Okay. Let's look at how does low water content have an effect. When the water content is low, your soil is stiff. It's hard to break the cloth. It's stiff. Okay. You provide energy. It's very hard to work with such a soil. The grains they offer resistance to the energy which is applied. Okay. In other words, it's very hard to bring the particles together, closer together. So you have a lower, a low dry unit weight. Low particles are packed over here. As I move along this curve, meaning I move down this arrow, the water which is now added, provides a film around it. So this film of water kind of tries to lubricate the soil. This lubrication effect helps to bring the particles closer together. So closer together to form a denser configuration. If it's closer together, your dry unit weight starts to increase. So no wonder your figure goes way up somewhere here. So what happens if your water content reaches close to the OMC value somewhere here? When it reaches close to OMC, the lubrication effect is maximum. So somewhere over here, that's at OMC, the lubrication effect is maximum. Your particles are well close to each other. They are well packed. And if I move beyond the OMC, now the water, which is now too large a quantity, it starts to occupy the space which otherwise would have been occupied by the soil particles. Now because water occupies the space which otherwise would have been occupied by the soil, I can clearly say the unit weight has to fall because water has a lesser unit weight compared to the soil. So if water now goes in and it replaces the soil, my dry unit weight of the material is bound to decrease. So no wonder you get a drop in the curve after the transient peak. Some people, for example, if you follow the book by Lamb and Whitman, they have a different way of explaining this. And I like this procedure, which, it's more, I would say, it's a better way. I wouldn't say it's a better way, but it's something which tries to explain how the clay particles, the fabric of the clay particles which we have studied, how it affects. Okay, let's look at this fabric and structure of the clay which we are familiar with. If you recall in the previous class, we say clay and water are dipolar. Okay, that's what we have seen. And a film of water which is adsorbed, AD water, which forms a layer of film of water all around. Okay, so having this background, let's look at how the water content affects. So we have the same scale as in the previous, one of the previous slides. Water content increases as we go down. And the idea is, how does the clay fabric change? Remember this inverted parabola, we are looking at only for the clay behavior, not for silts, not for sand. So this, what we are looking at on this slide is for clay. Okay. So at low water content, somewhere here, when you're somewhere down there on the curve, okay, somewhere here, remember these are the lines. These are more sleepy lines. These are random lines. So at low water content, the thickness of the adsorbed layer, because the adsorbed layer is not fully developed. If it's not fully developed, the surface is no longer negative. And because of the dipolar nature of soil particles or the crystals, there is high attractive force amongst the clay crystals or clay particles. High attractive force means the soil particles tend to flocculate. Flocculate is randomness. They are randomly placed, okay? And it's very hard to work them, to bring them closer because they already have attractive force, and with the energy we provide, it's hard to bring them closer. That is why you have a low dry unit weight somewhere here or low density, okay? What happens if I increase the water content, meaning as the curve moves forward? Okay, as the curve moves forward, okay, I have the same figure which was shown in the previous slide somewhere here. I've pulled it towards the top. The low water content we have discussed, and now we're going to discuss how the water content increases. If the water content increases, the double layer or the layer of adsorbed water, AD water, gets developed. Or if it gets developed, in other words, the film around this clay crystal is now more negative. There is more negative at the surface, or there is more repulsive force starts to come in. Okay, there is more repulsive force. In other words, the soil particles which are flocculated now tend to be more dispersed. The randomness is no longer there. The lines are now becoming more of sleepy lines. I hope none of you are asleep right now, but the lines are sleepy. Okay. So in other words, the particles, more particles can be packed in the same volume because the randomness is not there anymore. And at OMC, the diffuse double layer or the layer of adsorbed water is now fully developed. Okay, it's fully developed at OMC. If it's fully developed, in other words, the maximum particles can be packed, have been packed, and no more particles can be packed beyond this. And beyond OMC, the reason given by Lamb and Whitman, okay, if you happen to look at the textbook by Lamb and Whitman, is reason given is similar, meaning the water tends to occupy the space which otherwise would have been occupied by the soil grain. So water takes in space, so dry unit weight starts to decrease. There are less soil particles available. Move on to the next slide, okay, which discusses the compactive effort. So up to previous slide, we looked at how the water content, change in water content changes the compaction curve. Let's look at the compactive effort. How does it change the compaction curve? With the increase in compactive effort, so that's take an example of this curve at the bottom. Okay, it's reddish color, I guess, and this shows light compaction. So if I use the heavier compaction, so if I increase the compactive effort, that's the curve shown over here, yellow. What it shows is my dry unit weight, the maximum dry unit weight has increased. It was here, now it's there. The second and important thing to note is my optimum moisture content or optimum water content has also decreased. So from here, it has gone back. Okay, that's an important statement. Okay, so these two curves are for different compactive effort. It's also noticed that change in compactive effort has not changed the intercept of the zero air void line. That's the zero air void line. So I repeat, no matter you change the compactive effort, this line can never be hit. You can never hit by this parabola. Move on to the next slide, please. You're looking at compaction curves for different soils. So with the same compactive effort, what happens if I move the soil from well-graded soil down to medium gradation and then going down to poorly graded sand. So all these are clay, CL, CI. I hope you have done classification, but if you have not touched classification, let me start that these are well graded, top 3 are well graded. So if I look at well graded soil, that means most of the particles are present. I have a curve which shows a higher dry unit weight. Okay, 1, 2, 3, high dry unit weight. Okay. If I look at the clays you will find that the clays have lower dry unit weight, but it's important to note all these curves which contain clay, they need more water, they're hungry for water. Okay, so the optimum water content or optimum moisture content is also high. Okay, so they're hungry. Look at the last one, poorly graded. That's somewhere here, I suppose. That's the poorly graded. Okay, you can hardly identify this as a compaction curve. I would say it's very poor. It's hardly compactable. But the best curves are obtained somewhere here, okay, wherein you have some amount of shape, inverted parabola shape being visible. Move on to the next slide, please. It leads us to understand how does the compaction curve for sand behave. Okay. Compaction curve, it's interesting to note the compaction curve for sand. So if I have vertical axis as dry density or the dry unit weight, horizontal axis as water content, surprise, surprise, what you see is that the dry unit weight initially starts to decrease with the increase in water content. Okay, why would that happen? Okay, if you happen to study or I would say look around and if you go to a material supplier who sells sand, if you go and buy sand, the sand which usually you would see in the shop of material supplier would be somewhat moist. That moist thing is what it causes. The moist thing causes is it causes the soil to bulk, or to put it in more scientific way, there is soil capillarity which comes into picture. Soil capillarity means the individual soil particles are held together by film of water and the water tries to climb up. That's soil capillarity for us. We will look at this later when we study soil capillarity and permeability. But the idea is you have soils wherein because of soil capillarity, the same energy you're not able to break it off. So what happens is because of the development of soil capillarity, the particles are not able to come closer, or you have a decrease in dry unit weight. Somewhere beyond about 8% or so, I guess this is roughly 6% or something like that. Beyond this value, the soil capillarity is broken, and then your soil particles start to come closer, okay, with the increase in water content. And then you see that the dry unit weight starts to wobble or fluctuate around when it reaches a degree of saturation of 1. So somewhere here you'll find the degree of saturation is close to 1, and somewhere here the degree of saturation is air drier, let's say it's nearly 0. It's quite important to note that the dry unit weight is nearly similar. So in other words, if I have a completely saturated soil, completely dry soil of similar dry unit weight, its mechanical properties have to be similar. Okay, that is why many people argue. If I do a test on completely dry soil, it has a similar behavior as a complete saturated sand. I speak about sand over here. So saturated sand and dry sand should have similar mechanical behavior, and this is true. Okay, this is true. So just to put it in English, what we have said, at low water content there is capillary. This capillary causes bulking of sand, and I have a number 4 to 8%, but it can go up to 4 to 5%, but it can go up to 8% in some cases. So that's bulking of sand for us. Okay, if I increase the water content, the menisci or the soil capillary is broken and the particles are able to come closer. Okay. If I move on, further increase in water content results in fall in dry unit weight. Okay. That's when it reaches saturated water content. In fact, you are able to see the wobbling thing. That's somewhere over here. Okay. This we have just said. The difference in the dry unit weight of sand when it's dry and when it's saturated is similar. I'm going to skip this. We have just said so. The next one is method of compaction. Okay, I would not like you to look at the numbers or the figures, but what it shows is these numbers 1, 2, 3, 4, 5, 6, 7. These are different methods of compaction, and these different methods of compaction, it shows, have produced different curves. So there is no unique curve for the soil. In other words, the field compaction which we see, if I say, okay, if I say this curve is more suitable, no, someone can argue the other curve is more suitable. So the field compaction procedure it's very hard to simulate in the lab. And we mainly stick to our IS light compaction or IS heavy compaction, which is similar or akin to Proctor compaction and modified Proctor. So we are not able to really reproduce or really produce the correct value or the value which should be available in the field. The next is, how about the structure? Now this is important, and somewhere over here we are going to, towards the end of this, we will stop and pause. Let's look at the structure of the soil. Structure, we are more familiar with the term fabric. Okay, so fabric is something we are familiar because it speaks about orientation. We say dry of optimum, that's somewhere here, the fabric is flocculated, there is randomness. And wet of optimum, the fabric is more, there is more orientation, or the fabric is dispersed. Okay, this is something we have seen. What happens if you increase the compact effort, meaning compare the fabric at A and the fabric at E? There is higher energy at E, which shows that the orientation or the randomness is now reduced. There is more regularity which now exists at E. In other words, the flocculated which was at A is now less flocculated at E. Likewise, C is more, is less dispersed than E. E is more, apologize, this is D. D is more dispersed compared to C. So there is more regularity. The sleepy lines are more regular at D. That's how the difference. You increase the compactive effort, your regularity starts to increase. The particles become more regular. So just to put it in English, these are the things written, and I'm going to skip this because I would like you to read it at home if given a chance. Just to put it in English what we have said. There are 2 or 3 engineering behavior which we are going to look at, and the first one is the permeability. Now this figure over here, the bottom figure shows the dry unit weight versus water content. That's the somewhat a parabolic kind of figure. Okay. Compare this to the permeability. Look at the permeability, the water content. As the water content increases, so for each and every mold, we have measured the soil permeability. So somewhere here is we measured what is the permeability. And as the water content increased, we prepared the mold, and the same mold which was prepared for Proctor, we did this permeability test. Okay, remember, permeability test would have been done when the soil is, somewhat try to saturate the soil by passing huge volumes, 4 volumes of water. So this test was probably done on a saturated soil. So this, it shows that the water content, initial water content was here and increased because of saturation. Now that's not the focus of this slide over here. The focus of the slide is, for each mold we measured the soil permeability. So as the compaction curve went down, the soil permeability was shown to decrease by nearly 2 order of magnitude. That's 1 order somewhere here and another order over here, and then beyond a minimum value somewhere here, this minimum value was beyond the peak. It's important to note that the minimum permeability is not at the maximum dry unit weight. Minimum permeability is slightly beyond the maximum, and somewhere here the permeability again starts to increase. Now I would not like you to, we don't have time to go through, the reason behind it, but for at least for the sake of completeness, I would like you to remember that the permeability is minimum somewhere beyond OMC, and it's approximately about 2% beyond OMC for most of the soil. So in other words, if I have to prepare a dam of clay core, an earthen dam made of clay core, I would compact the soil be somewhere beyond OMC. That's about 2% beyond OMC, so that the permeability is less. move on, please. I'm going to skip this slide, please. The next one is compressibility, and it's important to note that how the soil particles compress as the uh, load or the applied load increases. We have about 8 minutes left, and there are not many slides. What I suggest is we do this next time. Next time I'll prepare a problem sheet. I'll bring in 1 or 2 problems on this chapter, this section on compaction, and we'll also manage to complete this particular part. I am giving about 8 minutes for any questions. If there are questions, we'll take some questions right now. If not, we will probably spend 5 minutes to complete this. But I'm more happy if you have questions to ask. Go ahead, please. Questions, please. You don't have questions, I have a question. I will ask you. Any question, please? Okay, thank you. We have AITM teacher.
Sir, good morning, sir.
Good morning.
Good morning, sir. I am Hamantra from Aditya Engineering College. Sir, which type of structure that we find exactly at the OMC condition, sir? Which type of structure that we find in the soils exactly at OMC condition?
Okay, that's quite interesting. I didn't think about it, but I would presume that it should lie somewhere close to the dispersed. Somewhere it should be close to dispersed at the OMC. I
Sir,
speak about
in case of some cement stabilized soils, we find maximum strength for the soils at wet and optimum condition. Why like that, sir? In case of some cement stabilized soils, we find the maximum strength for the soils at wet of optimum, not at exactly OMC condition. Why like that? Cement
so?
stabilized rattles, I mean.
Okay, I'll repeat your question. Your question is, in cement stabilized soil, you see the maximum strength somewhere beyond the OMC, okay, and not OMC
Yes,
or
sir.
before OMC, right? Now, I'm
Yes,
quite
sir.
surprised to listen to this, because cement stabilized soil will normally create a sample which is brittle. It will brittle, and somewhere beyond OMC, your soil sample should be more ductile. So if I do I presume you speak about unconfined compression test on cement stabilized soil. If I do a test on UCS test on the soil, I would expect the soil to be more brittle. In other words, the soil should be at OMC or less than OMC. The strength is maximum. Most of the data shows that the strength is maximum at OMC. Okay.
Sir, what is the
Beyond OMC, the strength becomes more ductile and not brittle. So I would say if you have some data which shows that the strength, you are still able to have good strength beyond OMC, I would say look at the curve. The curve would normally, beyond OMC, the curves would normally be more flatter. It will not immediately break off. And before OMC, you will see that the sample just breaks off.
Sir, what is the effect of this agglomeration mechanism in case of this stabilized soils, sir? I mean, what is the effect of how it affects the OMC and MDD? The agglomeration mechanism, which is taken place in case of stabilization of soils.
I'm afraid I think I will not be able to answer this.
Sir, we find the agglomeration mechanism in case of stabilized soils.
What mechanism?
We cannot understand. Sir, my voice is clear.
Your voice
Sir,
is clear.
agglomeration mechanism, sir.
Accumulation. Okay.
Sir, we find agglomeration mechanism in case of stabilized soils. Hello,
Yes.
sir.
Yes, I can
So
hear
what is
you.
the effect of this agglomeration mechanism on OMC and MDD? What is
I
the
I
effect of agglomeration in case of
I
on OMC and MDD?
I do not know. I can't. I do not know. I'm sorry.
Mhm.
Okay.
Okay, sir. Thank you.
Thank you. Thank you. Okay, we have the DT KIT teacher.
Morning, sir.
I hope your question is
So
more
note
related
that
to
for most
boundary soil mechanics and not ground improvement procedure. Please tell me, please.
sir, for most of the stands, the value of dry weight rate and saturated weight also always of the same.
माइक को थोड़ा नजदीक ले लो माइक को थोड़ा नजदीक ले लो
Audio is okay. Why is it not clear? Yes. Can you please repeat what you said?
So you showed a slide in which the volume of sand you showed. That slide, so in which I want to know that for most of the sand, either they are coarse, very coarse or coarse, the value of dry weight, which was Rodi, and the saturated dry weight, they always want the same, or there is a little bit variation in their values because the mechanical properties depend on most of the density. So I want to know.
Okay. I think your question is. Okay, I think your question is whether the maximum dry unit weight for a dry sand and a saturated sand is similar. Is that your question? The camera now, your camera now faces your colleagues who are sitting over there. Please let the camera face you.
Yes.
Okay. Now this is true. This is exactly your question is correct. The maximum dry unit weight of a dry sand and a saturated sand is similar. That is why, if you want to do a relative density test, a relative density test is recommended to do either on a dry sand or a saturated sand. Okay, both the results nearly give you similar. Was that your question?
So the method of compaction for both of the sand should be same or not? So my question was that for most of the this is that the method of compaction for both of the sand should be same or not? Because for the granular cells we use vibration techniques and for
Yes.
is the sand will be saturated sands or not?
Okay. The curve which I showed, in fact, was for, if I use a Proctor test for sand, but usually you would not do a Proctor test on sand. You would only do a vibration test using a vibratory, a plate. You for compaction test for sands are never recommended. You do a different test altogether. You do a relative density test. So in this case, okay, please let me continue. In this case, the example was given just to show that if you are given a sample of sand and if you want to do a Proctor test, how will the curve look like? Was it clear? Was I able to answer your question?
Sir, I'm not able to see properly.
You know what? Are you able to hear me very clearly? Just wave if you can. Very good. Because over here your audio, I'm just trying to make up your question based on the audio. Your audio is extremely coming out to be what do you say? It's overlap. There is overlap of audio. Uh,
Sir, I want to know, sir, that for all type of science, we use the validation techniques, always either they are in any condition.
Okay, sands usually you would not do compaction test. Sands you would only do relative density test. Could you put your question on chat? That becomes easier. I can easily read out. Can you put your question in chat? There is just put your question in chat. It will help. Okay. Go to the next one, please. Okay, please. GCT teacher. I don't see anyone has a question. There's no mind. Is this the same one?
Hello?
Please.
Hello? Hello?
Yes, I
Hello?
I can hear you. It's slightly audible.
Good morning, sir.
Good morning.
Sir, the soil is compacted soil at OMC. The sample prepared at OMC is consolidated or not?
So your question is whether a soil sample prepared at OMC is consolidated.
The sample is prepared at OMC and fully compacted.
Yes.
The consolidation test is
Good morning, sir.
Good morning. Tell me, please.
Can consolidation test be carried out in a sample prepared at OMC by Proctor test, sir?
Okay, if you want to do a consolidation test on a sample which is prepared at OMC, is that your question?
yes, sir.
Whose mobile phone is it? Okay. See, normally if you prepare a sample at OMC, it is not saturated. You would have to saturate the sample before doing a consolidation test. Okay. Otherwise, the results of consolidation test will not be valid. So what people do is, they allow water to permeate through the sample. After compaction at OMC, they allow the water to permeate through the sample, to allow water to permeate by say 3 or 4 volumes. So when I say 4 volumes, it means you calculate what is the volume of voids in the sample, and that much water you just allow the water to permeate. Maybe 3 or 4 times that. And then you have to do a quick trial test first and then measure the water content. If the water content shows that the degree of saturation is 1, then that much pore volume is correct, and you would have to then work your way backwards. But if I prepare a sample which is at OMC and I start doing consolidation test, the results will not be valid. I have to first saturate the sample, and one of the ways is water to permeate through. If you have an equipment in which you can allow water to permeate at high pressure, like similar to a triaxial test, that would be much better. It is fine in saturation. I hope I was able to answer your question.
Yes, sir. Thank you, sir.
You're welcome. Thank you. Is another question?
Sir, good morning, sir.
Yes,
Hello.
good morning.
Good morning, sir. Can you hear me, sir?
Yes, I can hear you.
Hello. Sir.
I can hear you.
Hello, sir. Sir, if we add the water content, yes, sir. If we add the water content more than OMC, what will happen to the structure of the soil, sir? How the structure of the soil will vary? The more addition of water content to the soils
Yeah,
in case of fine grained soils. Sir, more addition of water content to the fine grained soils like silts and clays. What is the effect of structure? I mean, how the structure will vary in the soils?
yeah,
How the structure will vary in the soils?
yeah. So your question is, how does the soil fabric vary if I increase the water content beyond OMC? Is that
Yes, sir.
correct?
Yes,
Now,
sir.
at OMC, the soil fabric is nearly, nearly dispersed. It has nearly reached a dispersed level. I would say you would, your fabrics should remain, my guess is it should remain more dispersed, but the fabric would not definitely change very much. It remains dispersed because already you have reached, you have removed all the attractive forces. So now because there are more repulsive forces, you have reached a fabric which is more dispersed.
Okay, sir. Thank you. Thank you, sir.
Welcome. Thank you.
Thank you, sir.
Okay, one last question from DCRU, please.
Good morning, sir.
Good
Good morning,
morning.
sir. So
Yes,
my
good
question is
morning.
that, yeah, sir, I am having one query regarding this consolidation and compaction. So if I do the consolidation on a sample of a same soil and do the compaction with OMC,
Somehow your audio is lost. I could hear only up to compaction of at OMC. Beyond that, your audio was lost. I am not getting any audio, please. Can you check your end, please? There is no audio. Can you please check your mic? I'm not getting any audio from your end. Is it the mic problem or any other? I am not getting any audio, sorry. Can you put your question on chat, please? Quickly, if you can put your question on chat. This is the one. Wait, I think. This is AI. Uh, I'm afraid that we have still not got your question on chat, please. We got it. On a given, the question is, on a given sample of soil, if we do the compaction at OMC and consolidation on the other hand, in which case we will get higher dry density. I'm not able to get your question well, but I'm not able to clearly understand. It says if I prepare a sample at OMC using compaction test, and if I prepare another sample using consolidation, which will give me a higher dry density. Do sample of soil compaction at OMC, consolidation on the other hand. See, compaction is consolidation is only for saturated. That's what basic understanding is. So you're taking two soil samples. One is you're doing a compaction test. The other sample you're doing a consolidation test. And if you tell me if I apply some a similar load on compaction to prepare a sample at OMC, and if I apply a constant or a similar load on a saturated soil to prepare a sample with consolidated sample, and if you ask me which has a higher density or higher unit weight at the end, your guess is as good as mine. I have a feeling that there won't be a unique number. Both the answers can be same and may not be the same, because you are actually doing entirely different procedure. So they may not have the same answer, and it is not that the one may be higher than the other. So there is no unique answer for this. I'm afraid this is all I can answer. Okay, I hope this is the end. Could you, I mean, please, we have to close this session now. Could you please email this to me and let me think about it. If you have a question which you'd like to clarify, DCRU, please email this to me. I have to close this, but there are people standing behind me. Thank you. Okay, your question is, if I have to construct an embankment, do I go for consolidation or compaction? Believe me, if you have to do an embankment, if your soil is saturated, you can never do compaction. If you would have to dry the soil to do compaction, and then doing a compaction would be much better. I would say then doing consolidation, because your results are immediate. You would, if you want to do consolidation, it may take a few months to achieve the similar density or similar strength which otherwise you would achieve using compaction. But then again, for compaction you need to dry the soil so that it is not saturated. Otherwise you will not be able to compact the soil. Okay? I hope I was able to answer this. Thank you.